Okay, for this video, I'll be going through Pure Physics Chapter 19, Electromagnetic Induction, Success Criteria B. So, describe a simple AC generator, either in the form of a rotating coil or rotating magnet. So, and the use of slip rings where needed. So, if it's a rotating coil, that means the magnet is stationary. Okay. And if it's a rotating magnet, then the coil will be stationary. Okay. Now, before we start to go into this AC generator, okay, so whenever you see AC generator, you must think of Fleming right hand. Okay, Fleming right hand rule. Okay, so there are actually three people involved in this chapter. The first one is Faraday. Okay, so Faraday actually did experiments and found that whenever there's a change in magnetic field experienced by a coil or conductor, okay, then there will be a induced current produced. And the magnitude or the size of the induced current depends on depends on the rate of change of magnetic field that it is experiencing. So for this induced current, right, it brings in two other people that are involved in this chapter. So the next one is actually your Fleming. Okay, so Fleming, when he uses when he uses Fleming right hand rule, okay, he can actually predict direction of induced current. Okay, that means he will know the direction of the induced current, or you will know what is the direction of the induced current if you apply his Fleming right hand rule. Okay, which is to show that the thumb represents the force. Okay, then the index finger represents the direction of external magnetic field, and then the middle finger actually represents direction of current. So if you know what is the direction of the force or direction of motion that the conductor moves, and if you know the direction of the external magnetic field, okay, out of these two, if you know all this, then you can know what is the direction of current. So he can sort of tell you what is the direction of the induced current, but he cannot explain it. So to explain, he can't explain. To explain how, or to explain why the induced current flows in a certain direction, okay, you actually have to rely on Lenz's law. Okay, so Lenz's law is that the direction of induced current, okay, we are talking about induced current, it will be to flow so as to oppose the change producing it. Okay, so as to oppose the change producing it. That means if I have a magnet north here and I have a coil over here, okay, if the magnet is moving towards the coil, the solenoid, then there will be a north pole induced here, or there will be a north pole on the side that is facing the incoming north pole, and this is because the induced current will flow in such a direction to oppose the change producing it. Okay, so these are the three characters in this chapter. So Faraday will explain why there is an induced EMF. Okay, because there's a rate of change of magnetic flux experienced by the conductor. Fleming will be able to tell us what is the direction of the induced current, and Lenz's will be able to explain why the direction is in such a way. Okay, so this was what we have covered in success criteria A. So now let us go into this AC generator. So we consider the case of a rectangular coil that is mounted on an axle rotating between two permanent magnets. Okay, so due to the rotation, the coil will experience a change in magnetic flux. So if I were to draw out the 2D of it, and if I were to put my eye here, I would see AB over here. I would see CD like this, right? Because I'm looking at the cross-sectional view. So these are the magnetic field lines of the external magnet. So as the coil is turning, right, I'm providing the force. In this case, I'm making the coil turn in a clockwise direction. That means AB will go up, CD will go down. So as AB is moving up, it will cut the magnetic field lines. Okay, so in success criteria A, I show that it cuts, doesn't cut, and doesn't cut. So something like that. There will be a change in magnetic flux experienced by the coil, and according to Faraday's law, whenever there's a change in magnetic field lines experienced by the coil, there will be an induced current. Similarly for CD, as it goes downwards, okay, I'm providing the force and there is an external magnetic field, there will be an induced current produced because there will be a change. But once I stop turning the coil, okay, there is no longer a change in magnetic field lines experienced by the coil. There is no more change. But is there still magnetic field lines experienced by the coil? Yes. Okay, just that there's no longer a change in magnetic field lines experienced by the coil because the coil is no longer rotating. Okay, so this is very important. There must be a change in magnetic field lines experienced by the coil. So then there will be a continuous flow of current induced in the rectangular coil as long as I keep on turning the coil. So the direction of the current is given by Fleming's right hand, but we are not able to predict, we are not able to explain why it's like that. Okay, so maybe we can use, let me clean this up. We use AB, and so this is AB. We are going to apply using Fleming right hand rule. So this is the force on AB. This is a force on CD, right? We are the one that is rotating it so that it can turn in a clockwise direction. So now for this instance, whereby AB is over here and we know that the force is upwards, we'll be using our Fleming right hand rule, and if you have applied correctly, the current will be into AB. That means it will be flowing from A to B. Okay, that means let's apply the Fleming right hand rule again to CD. So the magnetic field is from left to right, so my index finger will be pointing from left to right. My force is downwards to the bottom of the page, and that will give me a current represented by the middle finger, and that will be current flowing in CD. Okay, so the current will flow in a continuous loop. Okay, and once it has turned half a revolution, okay, so I'm going to draw N. After turning for half a revolution, AB is here, CD is here, and because I am always turning in this clockwise direction, of course you can turn clockwise or anti-clockwise, but but you will want to keep it in one direction, so it's easier for us to turn, right? So now that half a revolution later, CD is on the left hand side nearer the north pole of the external magnet, AB is on the right hand side. Okay, and because we are turning it in a clockwise direction, now CD, at this instance, the force on CD will be up. The force on AB will be, should be CD. The force on AB will be downwards. So we apply Fleming right hand rule, and the current will still be in the same direction in the coil, but opposite for arm CD as previous and opposite for arm AB as previous, right? So if you compare AB when it was nearer the left hand side, the current is into the page. Now AB is nearer the south pole. On the opposite side, the current is actually coming out. Okay, but overall the current will still be flowing in the same direction. If you look here, the current will still be flowing in the same direction within the coil. Okay, so as the coil flips after half a revolution, the induced current changes direction and is now flowing from D to C to B to A. Okay, and we will need to look at the resistor this time. Okay, so let's look at this at the start. Because the current flows this way, and by the way, these are the slip ring commutators. So this slip ring commutator is attached to AB. Okay, I hope you can see this. Okay, this slip ring commutator, if I color AB as blue, okay, this slip ring will be for AB. Right, it is hardwired to the side of the arm of the coil that we are talking about. And if CD is green in color, then you see that it is hardwired to the second slip ring. Okay, so each of this arm has its own sort of slip ring commutator. Okay, I think it's a little bit similar to the motor, whereby each arm has its own split ring. Okay, each arm has its own split ring. So what does this mean for us? So we see that the current is going from A to B to C to D. Okay, and if we were to trace out the direction of the current, it will be in this direction. Let me use a different color. It will then be flowing in this direction. Okay, yep. Okay, it will be flowing in this direction. Therefore, sorry, I think I made a mistake here. Yep. That means for the resistor, right, the current, because the resistor is fixed, so current always flow from higher potential to lower potential. So here will be positive, here will be negative, right? The current is flowing from this point, if you like, let's call it X, to this point to Y. So through the resistor, the current is flowing from X to Y. Okay, but after half a revolution, okay, the current is now flowing in this direction. So this was point Y and this was point X. Okay, and the current now is flowing from Y to X, opposite from the previous, whereby it's going from X to Y. So even though the current, look at this blue color cycle, the current is flowing in the same direction within the coil. The coil is turned in the clockwise direction. The current is still flowing in the coil in the same direction. Okay, but through the external resistor, there is a switch in direction of the current, and therefore this is a alternating current. Okay, so an alternating EMF is produced by an alternating induced EMF. So when the coil passes the vertical position, wires A and B and AB and CD move parallel to the magnetic field, so they do not cut the magnetic field lines, and hence no induced EMF or current is produced. Okay, so what's the structure of an AC generator? It is a rectangular coil of wire mounted on an axle and placed in an external magnetic field. Okay, then we have these slip ring commutators. These slip ring commutators, there's one for side arm AB, there's one that is sort of belonging to arm CD. Okay, so it is connected to the coil to enable the direction of the induced current to change in the external circuit at every half turn of the coil. So this is something like your motor, whereby the direction of the force is is facilitated by the split ring commutator. Okay, so that the direction of the turning of the coil in the motor will be continuously in one direction. Okay, I will do a comparison between electromagnetism and electromagnetic induction, because there is both a coil, but for electromagnetism it is a split ring. For electromagnetic induction it is a slip ring. Okay, so the slip ring enables that the end of the rotating coil do not get twisted together, right? Something like a split ring. And they also provide the electrical contact so that the electric current can flow continuously. So what's the purpose of the carbon brush? Is to provide a sliding contact. So this is what we have in the motor as well. So to enable the induced current to flow out to the external circuit. Okay, resistor is used to prevent high current from flowing back to the coil. Okay, so this is for success criteria B.